In this video, we're going to talk about 3 special cases that can happen with respect to the results of linear programming. We're going to talk about alternative optimal solutions. We're going to talk about infeasible solution, and we're going to talk about unbounded solution. So out of these 3 cases that we're going to talk about, the first one, alternative optimal solution, solutions. This is usually a good thing for decision makers. This is a good thing for managers. But infeasible solutions and unbounded solution, the other 2, these are not good for managers. So in those 2 cases, you actually cannot find an optimal solution. You don't have a reasonable finite solution, right? So these 2, in the case of infeasibility and unbounded solution, what we usually need to do is to go back to our formulation and correct the problem. For the case of alternative optimal solutions, our challenge would be to find the alternative optimal solution. It's usually great to have more than one optimal solution, but the problem with Excel solver is that it only shows one of them. So it's up to us to go ahead and use some tricks to be able to find other alternative solutions. All right, so let's go over them one by one. So alternative optimal solutions. For the case of linear programming, when everything is in the linear form, is set up in the linear form, and all the variables are continuous, like with the examples that we have seen so far, it can only happen where the optimal objective function contour actually is parallel with one of the binding constraints. So if that happens, then we will have multiple solutions. When we have actually a line, let me just show you the next slide, the example with the PAR company, parking corporation example that we talked about. If we just change the objective function and make it parallel to one of the binding constraints, what happens is that all the points, before we had the optimal solution, the maximum point on one corner, but now when this is parallel with this line, which is one of the binding constraints, what happens is that it's not just one corner anymore. There are 2 corners, corner 3 and 4, that are optimal. And indeed, any point in between 3 and 4, any point on this line, if you plug them into this equation, 4.3 times S plus 9 times D, the result will be always 5670. So any point, both these corners, 3 and 4, and any point in between, when you plug them into this equation, the objective function, it always gives you the maximum point, which is 5,670. So any point on this line from point 3 to point 4 is indeed an optimal solution. So this is really what we mean by alternative optimal solution. There are more than that. There are more than just one. But when it comes to Excel solver will show you one of these 2. I mean, either of these 2, 3 or 4. And from the report, from the answered report that we get from Excel, there's no way that you can find that there is, first of all, there is an alternative optimal solution, and second of all, what that alternative optimal solution is. So, but there are some ways that we can look for alternative optimal solution and see if they exist. It's usually a good thing to have an alternative optimal solution because it gives more options to the decision makers and to the managers. The next special case is when we have infeasible solution, infeasible solution or infeasible region, which basically means that there is no feasible solution, there is no feasible region. And if there is no feasible region, there is no solution that can satisfy all the constraints. There's no point that can satisfy all the constraints. If that is the case, then how can we find an optimal solution if there is no point that actually is feasible? Because if you remember the way we solved the way we solved it, we solved our LP using drawing method, or the way actually the simplex method works is that it always looks for the corners of the feasible region. So there has to be a feasible region before you can go ahead and look for the best point in the feasible region. So if there's no feasible region, it means that there's no optimal solution. And in those cases, infeasibility happens. The problem, the cause of this problem is that usually you have put too much restriction on your model, too many constraints, and constraints are too tight. So what you need to do as the analyst here is that just go back to the manager and talk to them and explain that the constraints that you have put in your model, they're so restrictive and you have to relax some of them. So here, infeasibility means that there are constraints that do not, there's no overlap between them. They're completely opposite to each other. So you have to make some compromises here. Example of that, again, in the same example, the PAR incorporation problem, we had, I mean, if this was our original feasible region, but let's say if we add these two constraints, two new constraints of a minimum production requirement of 500 standard bags. So this is standard bag, 500. So we need more than 500. And we also, if we require having more than 360 of deluxe bags. So what happens is that this is the sub-region satisfying the minimum production requirement, and this is the original feasible region. This is the actually the feasible regions with the available amount of resources. And as you can see, there is no intersection. There is no point that can satisfy both of them. And that means we are not actually able to satisfy all these constraints. So we have to, again, go back to the manager and to the management and make sure that we either relax these two numbers, our minimum production requirement, or we increase the amount of available resources. And that way you can bring up this region, all right? So in case of feasibility, infeasibility, we need to relax our formulation. The next, so I'll show you in an example when we have no feasible solution, what message you get from Excel. Excel will give you a specific message showing that there is no feasible solution. But before that, let's just talk about the last case, and then we go to Excel and see one example for each one. So unbounded is the next case, next special case. This is a case where there is no finite solution. I mean, usually when we're solving a problem, we're looking for a reasonable, finite answer to our decision variables. But what happens in the case of unbounded solution is that you get infinitely large value for at least one of your decision variables. That's not good. Or infinitely small for a minimization linear programming. So in this case, your objective function is minus infinity. Here, the value of objective function in optimality is positive infinity. That's not good. That's not what we're looking for. We're always looking for a reasonable, finite answer for our question. Of course, without violating any of the constraints, the solution does not converge to a finite point, and you can just keep increasing or decreasing your variable, um, and um, and it's still feasible. So that's not good. So feasible region in this case is not bounded. Feasible region can go to infinity. That's the main problem. And here I have an example that I'm going to show you in Excel in a bit. But let's see, for this example, x is greater than or equal to 2, y is less than or equal to 5. So x is greater than or equal to 2. So any point to the right of this vertical line, y is less than or equal to 5. So any point below this horizontal line. So this is the feasible region. And as you can see here, feasible region is unbounded. It can go all the way to infinity. There is no bound on the value of x. I mean, we know that y cannot go, y is between 0 and 5, but x can go any, so from 0 all the way to infinity. There is no upper bound on x. And an objective function actually increases without limit. As you increase x, objective function increases. And this is a maximization problem, right? So this is a maximization problem, and it increases, objective function increases with x. So that's not good. So what happens is that you will get an unbounded solution at the end. All right. So in the case of unbounded solution, again, the problem is with the formulation. What we need to do is to go back to our formulation and make sure to add some more restriction. The current formulation, when you get an unbounded solution, it's a signal that the current formulation is not restrictive enough. So you don't have enough number of constraints, or constraints are not tight enough. So you need to add some more constraints to make sure that the feasible region is bounded. So now I'm going to go to Excel and show you the message that you will get from Excel in case of infeasible and unbounded solution. I just said that when you have alternative optimal solution, our first special case, there's no way that Excel can tell you. I mean, there are some ways, there are some tricks that you can use for looking for alternative solutions, but in general, the answer report does not tell you if there is an alternative solution. But for infeasible and unbounded solution, Excel will tell you exactly if that is the case. So I'm going to just solve this one, infeasible. So this is infeasible is when there's no point that satisfies all the constraints. And this is pretty obvious. If x is less than or equal to 2, x cannot go over 2, y cannot go over 5. How come x and 5 should be greater than 8? So x and 5, if x is less than 2, y is less than or equal to 5, then x plus y, the maximum they can take would be 7, not 8. You see, so that is the problem. And they cannot actually be satisfied at the same time. And that is when we have infeasible region. We don't have any feasible solution. And then because of that, we won't be able to find the optimal solution. So let me just quickly do that. Decision variables. X and Y, and I'm gonna assign two blank cells, one for each one. Objective function. Again, one cell, 20 times X plus 10 times Y. And then the constraint X less than or equal to 2, Y less than or equal to 5, X plus Y, so sum of X and Y greater than or equal to 8. And then the non-negativity constraint. So let me just solve this. I go to Data tab, Solver, and if here we want to maximize G4 by changing X and Y, subject to the first two constraints, left-hand side, are less than or equal to the right-hand side. But then the last one, we have left-hand side greater than or equal to the right-hand side. Okay, and non-negativity, and then simplex LP. So let's see what happens. We are expecting an infeasible region message. So let's see what happens. Yes, solver could not find a feasible solution. And then again, same thing, solver cannot find a point for which all constraints are satisfied. Feasibility bound. So when this happens, again, you need to go back to your formulation and just talk to the stakeholders of the problem and make sure that you make these values, the right-hand sides and the parameters, reasonable. Or if possible, you may want to actually remove one or two or some of these constraints that you have in your model. So that's for infeasible. This is the message that you get. What you need to do. This means that there's no feasible solution, and you need to correct your formulation. Now, in this case, I want to, this is the example that we had. I just want to show you the message that you get in Excel. So let me just copy this back here. Yes, I just want to show you the message that you get from the solver. So the decision variable, X and Y, let me just remove them. Objective function is the same. 20 times X plus 10 times Y. And then the constraints, I have X greater than or equal to 2, Y less than or equal to 5. All right. And again, going back to solver, we want to maximize objective function by changing X and Y subject to X greater than or equal to 2, Y less than or equal to 5. Again, simplex and non-negativity. If we solve, now we expect to get, definitely there's an unbounded solution for this one. The solution, the X can go all the way to infinity and will go to infinity because of the maximization of the objective function. So let's see what message Excel will give us. The objective cell values do not converge. And again, there is even no report here. The objective cell values do not converge. Solver can make the objective cell as large as it wants. So there is no bounded solution. There is no finite solution. So you need to, again, come back here, add some constraints or make these a little tighter. In this case, it doesn't work. So you need to probably add another constraint. Like if you reduce this 2 to 1, or if you increase this, uh, this doesn't work actually. That's the problem. You need to either change this or add another constraint here.